In my capacity as the Honorary Secretary of AMSAT, I sometimes get phone calls from people I've never met and don't know who say, "Can you please tell me how to build a satellite?" And it's rather difficult to know what to say. And so maybe Phil is going to give us an insight into how to build a satellite. Phil is one of these guys who gets everywhere, and if you've been following these the ARIS QSOs of the last year with when Tim Peake was on, Phil tells me he was present at all but one of them, and was also did a lot of the software in the background, mainly to do with the video system, which I thought was fantastic. So many congratulations on that, Phil.
Thank you.
And I'll now let you crack on with your presentation. Thank you very much.
Thank you. Can everyone hear me okay? Yeah? Okay, so I'm going to talk to you a bit about the University of Southampton's CubeSat program. We've also got Susanna over here who's designing the firmware for us as well. So a bit about my background in the project. So back in 2014, you had Alec come and give you a talk on this. And at that point, we were designing it on they were designing it on an Android phone computer. So I was involved a bit with the high altitude balloon testing of that. So we sent it up on a few balloon flights with a large test rig on top of it. It didn't work very well, hence why we've moved on from that. Then I was still doing balloon flights at Space Flight Society in 2015. And at that point, Susanna got the Space Flight Society involved in building the ground station side of things. So I started designing the ground station, then started talking to the students about the communications, the electronics, and have sort of taken more of a role in that since, and are now helping program up these, which are the development computer and radio boards that I'll talk about a bit later. So the Astronautics research at Southampton, we've got quite a large research group doing a lot of stuff, particularly in these two areas here. So the space environment with the debris and modeling just how many satellites we can put up there, and also the effects of space weather as well. We also have a lot of development of the ion thruster engines, and we have our own large vacuum, thermal vacuum test facility for doing that there. So this is all, well, certainly the space environment is all simulations and theory at the moment, and the CubeSat is the idea. It'd be great to actually do something practical on this. So on the back of that, so the CubeSat is once the CubeSat's finished and flying, it's a vehicle for research. And the big thing was that we could support the research being done into the orbital debris by plotting its orbital decay as it comes down and using that to validate the models that they're currently working in the research. So we've got a GPS receiver on board that's going to give us accurate positions as it decays, and that'll be fed back into the models, and we can validate that research. We would also like to try out the ion thruster engines as well, but that was decided it was maybe a bit too ambitious for the first CubeSat, so maybe the next one we'll stick one of the engines on it. But the other side of this was actually the building of the satellite is a massive educational opportunity for all the students. So we've got masses of students involved, and all the student groups. We've got student groups, individual research projects, and internships who come in. They're given a component with a set of specifications, or they have to work out the specifications for themselves, and they then design and engineer that through, and then hopefully the component later flies in orbit. So it gives them something to aim for just beyond their final report as well. And the other thing is also in the same vein as the FunCube stuff, doing outreach and promotional on this, so getting more people involved. This has created masses of interest in spacecraft engineering, not just within the university, but also in external groups, and it's also used in the school outreach that the university does as well as something to talk about. And once we've got it up there, of course, we can also receive signals from it the same way teams do with FunCube, and hopefully send down pictures as well. So this is just a summary of the number of people we've had involved. This is actually a little out of date, because since then we've had summer internship with, I think it was 8 students on, and then we've just had a new group project start with another 8 students as well. So we're now up to about 80 students and staff involved in this over quite a long period of time. And this has also been across all the faculties in the university who don't normally work together on projects. So we've got, ranging from, of course, it's being mainly done by engineering and environment, which includes the aero side of things. But we've also got electronics, computer science. School of Art has helped out on a lot of the promotional material and artwork. And also physics on things like testing of the magnetometer and simulating the magnetics that it's going to experience in orbit. They've got involved on that. So this is the timeline of the last couple of years, basically. So the current generation of the project, after the Android phone was sort of put aside, the current generation started in about early 2014, and then we immediately got a couple of engineering groups straight on with mission design and working on the onboard computer. Then myself and the spaceflight and others got involved on a voluntary basis, helping apply our expertise to help the engineering groups going through with it. And then we've had a whole series of group design projects, individual projects, internships going through, and then these have continued through this year. So what we've got in the design so far is this. So going from the top, we have the GPS board sitting up in the top. We have a passive attitude control system. We have a Clyde Space battery that we bought off the shelf. We have an EPS board, which has been designed by electronics students. The telecoms and onboard computer, which is the derivative of both ECS engineering, and now a few of us in the Spaceflight Society have been working on that. Then we've got a camera in the bottom, a mechanical antenna deployment system. So this is using the same tape measure antennas that people have been talking about. And then in the bottom, the camera pokes through there, and covered with solar panels on 5 sides, on the top 5 sides. So the structure has been made in the university, and it's gone through all the rigorous treatment required for sitting on the rails in the launcher. And this has been put through all the tests that's needed. And this is the most finished part of the satellite so far, is the box it's going to go in, basically. But this is it assembled with basically none of the electronics in it. You've just got, that's actually the camera sitting in the bottom, and then that is a FET that drives the resistor that cuts a bit of cord around the antenna to allow it to spring out after it's launched. This bit that the antenna is on is actually 3D printed plastic. So that then sits in between 2 metal plates there and contains little holes for where the resistor goes and where the elements come through. And that's quite nicely made. And then there's a space in the middle for, as you saw in the previous one, a balun board labeled, which has a balun for the dipoles on it. So passive ACS there, permanent magnet in the middle, hysteresis rods around the side to slowly stabilize it in orbit as it goes through the magnetic field. Power system, so this has been built by the electronics students. Quite a nicely engineered board. We've got overcurrent protection on all the rails, and we've got a supervisor microcontroller there that talks to the main controller of the CubeSat, and the main controller can reboot voltage rails here and there. The overcurrent protection and battery regulation is all done in analog circuitry, so that's entirely separate from the microcontroller to minimize errors on that. And then, as I said before, we've got a Clyde Space battery. It's a 10 watt-hour battery. and then some nice pricey triple junction solar cells on the outside to maximize the amount of power that we get through that. We also get, this also reads all the voltage rails and gives us all the current per each voltage rail, current per each solar panel, etc., allowing us to get out the kind of interesting statistics that you've seen from the FunCube satellite. So the actual payload of it, the main payload is this, which is it's a Novotel space-rated GPS, which should give us good positions in orbit. Should also work with Galileo if Galileo is operational, but we're not quite sure about that at the moment. And then as a secondary payload, we've got this camera in the bottom. It's quite a simple camera, but it outputs a decent resolution image, has the JPEG encoder built in. So the idea is we're going to pull the data off that when we've got enough power budget to run it, and then downlink that data slowly in chunks, similar to the SSDV system that Wouter just talked about. And then we've got our main onboard computer board. This is a development board that's made up at the moment. We're still trying out the RF side of things, hence why there's a lot of big, bulky, heavy connectors on it. But we've got a ARM Cortex-M4 microcontroller with dedicated watchdog. And then we're using two CC1125, which are off-the-shelf ISM transceivers, doing FSK packets. The plan is that we're going to use their native FSK packet on the uplink with error correction within that packet, and then use MSK on the downlink with a software decoder on the ground. Then we're trying out a couple of different power amplifiers here and a couple of different filters as well. We're also trying out an LNA, but it looks like that's not going to be actually required. It's quite sensitive by itself. And then we've got some of the other chips on here. All of the buses to everything is isolated with the idea that if one device goes faulty, it doesn't bring down the whole bus for everything else. And we've also got voltage translation between these run on separate low voltage regulators to the main CPU. So there's also isolation there to try and stop noise getting into the receiver. In terms of other sensors we've got temperature sensors on this board, we've got temperature sensors next to the PA, and we've also got a 9-axis IMU, which would be there if it was soldered onto that board. So that will give us magnetometer and also spin rate and such, which will be good to know. So the end plan is that this board will just contain the microcontrollers, radios, and then whichever parts of these we've decided to use will be put in. The other thing I was going to mention was on the downlink. So the university also has quite a strong communications research department, which mainly do mathematical modeling of error correction and such. So a lot of stuff going into the new 5G standard. And we've had some ideas of some exotic algorithms to use on the downlink. So there is a plan to use polar coding or something similar on the downlink to try and maximize the data we can get over that. And we reckon, we're currently still playing around with the power amplifiers. Their efficiency changes quite a lot depending on the amount of power you're pulling out. So we haven't quite decided what point we want to run them at yet. But the idea is that will be variable. And then this 6 kilobits per second MSK, we reckon with our ground station that I'll talk about in a bit, we should be able to get decodes at 0 degrees on the horizon in the orbit that we're hopefully going into. And the idea is we're going to also make that configurable so we can turn up the data rate and just see what we can get, because obviously getting more images, getting more GPS data would be very useful if we can. And then just asymmetric to that on the uplink, LDPC coding, because it's a lot easier to decode on the microcontroller. So the ground station, we've found a site on campus to put the ground station up. It's nearly good. I mean, you can see out this side that there's quite a low horizon view here. However, behind the camera is a lovely building that we have called the Faraday Tower, which is very tall. It's supposed to be demolished, but they're not quite sure how to knock it down. So there's a chance it may happen in the next couple of years, in which case by the time this goes up, our ground station will have perfect coverage. Until then, we're slightly compromised to the east. But we'll make do with it. Otherwise, it's a good site. So we're planning to put on there two Yagis for VHF, UHF tracking, two cross-polarization Yagis. And then this ground station is mainly going to be run remote because actually getting access into this building at the top, it's technically a plant room, so getting permanent access to it is difficult. So we're going to want to run this over computer from a terminal in the same building. And we thought, well, in that case, we might as well do an SDR receiver, at which point, well, it's only going to be used for the CubeSat for a few passes a day. So the rest of the time, we could point it at other satellites and then have a public web SDR output where people could tune into whatever satellite it's currently looking at. And then if we wanted to look at a certain satellite, we can schedule it to do that one, else it would sort of have a priority list of tracking the highest priority satellite that's currently going over. That's planned. Still got to get it through university networking and everything, which might be the biggest challenge on that. But we'll see how that goes. So that would be receive on, so we're currently planning to do downlink on 2 meters and uplink on 77s. So that would be watching, we'd probably use a FunCube receiver for that, watching the 200 kilohertz of the 2 meter satellite downlink channel, and then have that available as a web SDR output. The uplink then, so just to get this working with our CubeSat, we'd be going for the same native transceiver that we're using at the high end, but then just putting a PA on it to boost the power up, because those chips are only 10 milliwatts out, which obviously isn't enough. So probably a couple of stages of PA to boost that up to a decent uplink power, and that would then also be controlled by the PC. However, so we don't really see a need to put in any permanent base transceivers at the moment. However, the University Wireless Society, the amateur radio club on campus, has several VHF, UHF based transceivers. And what we're hoping is that we can then have times when we can pre-arrange access up there, and we can go in, we can plug in IC7000 or whatever they've got available, and have a go at working some transponder satellites as well. Or for diagnostics, we can plug that in and use that instead of the SDR and other stuff. So the university is actually quite excited about this because they don't have any equipment currently to operate satellites. They get very excited about going up and seeing the stuff at Surrey with Chris Bridges, and seeing all the radios they've got up there and all their control room with their tracking. So they're quite excited about having their own thing that they can get students using. So there's currently a plan to get undergrads who are doing the relevant module, which I believe is Space Systems Engineering or something similar, get them licensed and operating satellites so that they can work with Doppler, so they can work with the tracking and get an idea of how this actually translates to using low Earth orbit satellites. And then also trying other satellites as well. So we had a look around for launch opportunities, and as Wouter mentioned earlier, we saw them. They've gone up quite a bit in cost since the project was first envisaged. So we found out about the ESA Fly Your Satellite program. And this is a program that ESA runs where universities can apply for a place. They're judged on on how cohesive they've made the team, they've made the management, basically how likely ESA thinks they are to succeed. And if you look good, then they offer support and mentoring to get you through all the design stages. They give you access to their test facilities up in ESTEC and other places. And at the end of it, if you get it all done to their specifications, they'll launch it for you, which is fantastic. And so the there was a call for applications in January of this year. This was long awaited. It's been a while, I think, since they did the last one. So there were quite a few applicants, but we put together an application, very long document, by March of this year. And then in April, there was a workshop where we sent a student team to talk to them about the current design of the CubeSat. They took along a few bits. They did a presentation to a panel there, answered a lot of questions of have we thought about this, have we thought about that. And then in May, we got a letter from them saying, looks good, you're in. So we're now on this program. So we were, at this point, we'd been pursuing paid for launch opportunities. And so we were quite on with doing the CubeSat. As I said, the structure, the ACS, the power board, all that kind of thing is finished, and as far as we know so far, pretty much flight ready. So we've been put on a faster track than usual on the ESA Fly Your Satellite. So we're currently entering the critical design review phase. So ESA is going through everything and going, this doesn't look good, you need to do this. This doesn't look good, you need to do this. But that's currently looking quite hopeful. We're churning out solutions to what's going on with that. So our GDP team, our group design project team at the moment, who started a couple of weeks ago, they're actually going out to ESTEC tomorrow to do some workshops on the back of the document that came back on that called an RID, which I can't remember what that one stands for. But they're going to go over, work through some of the issues we've had, and ESA's going to mentor them through fixing the issues and getting the rest of it ready. The group's task then is over the next 6 months or so to get the satellite through final integration and get it through the testing. And basically, at the start of next year, we need to send it off to ESA for them to test at their facilities. So we're quite lucky in that we've got our own facilities at the university. We've got a shaker table, we've got the thermal vacuum chamber. We've also got clean rooms in the electronics side. There's a lot of optics research that goes on there that requires the clean rooms. So we've got preliminary permission to use those, as long as we don't bring too many dirty bits of metal in, apparently. Have to clean them first. So we're going to do a lot of environmental testing. The students are going to be doing a lot of environmental testing at the university, making sure that bits work. There's a few bits that we've had some issues on so far and might require swapping out a few small things. But we're hopeful that that can be done in the next 6 months. Then at the end of ESA's environmental testing phase, they go through flight acceptance review. Then we hand over the hardware. They look at it and decide whether they are happy to fly it on their spacecraft or whether it's going to fall to bits. And then we're aiming for launch Q1, Q2 2019, around there, assuming this all goes to plan. So at the moment, there's a lot of testing going on of the individual components. Had a meeting last week with the guys who are doing the power board, and they've got a massive strip board rig full of load test for all the individual power board with a microcontroller to vary the load levels and check that the voltage doesn't change too much, and all the bits like that. And then sticking it on the shaker table, we've had getting the antenna deployment to work in the thermal vacuum is something that's taken quite a bit of work at the moment, and of course setting the test up each time takes a lot of time. But so that's making big use of our thermal vacuum chamber at the moment. Also a lot of, now we know what the electronics is going to do, planning exactly what we're going to do with it, and given our power budget, what we should be able to do with it and such. Going through, double checking the numbers of the previous student reports, and just testing the whole thing until it breaks is the plan. Well, then we have to build another one. But yes, ideally, doesn't physically break is the plan. So I think I've run through all that a bit quicker than I planned. Does anyone have any questions on particular parts of it? Yes.
Firstly, congratulations. I saw the team a few years ago at Cheltenham Science Festival. They were all looking a bit glum. It looks as though you've come a good way since then. My question is about the camera.
Yep.
For a passive stabilisation, you've got... I think somebody's looking for a microphone. Okay, for passive stabilisation, you've got the camera looking out at the bottom.
Yes.
I think that'll be good for, polar research? But probably not going to be pointing...
As far as I'm aware, they're wanting to get photos of Southampton from orbit.
Okay.
There may be better applications for it.
I think it will depend on which way they put the magnet in before launch, and that will be a big decision.
Okay, there is a lot of review going on to what the ACS is actually going to do and how long it's going to take to calm it down and such at the moment. And once we've got an idea of the outcome of that, then we should have a better idea of what that's capable of. One other thing that I was meaning to mention was so this project, as you can see, has taken a little while so far. And one of the things that Chris mentioned in his presentation yesterday was you have groups of students who come in, they do all the work, they do the documentation that's required for their report, and then they graduate and leave. And handling the overhead of handover between projects has been a big part of the work in this, and has added a lot of overhead to the work going through. However, it means that we can segment that work down. Each of the groups gets a good experience out of it. They get good industry experience of doing it. So on the education side, it ticks all the boxes. It just makes it into a long slog for someone who's there longer than the student projects, basically. Yeah. Yes?
How have you gone about funding the project, and roughly how much do you think it's cost across the whole time?
I'm not aware of any numbers. I haven't been involved on that level, I'm afraid. But there have been several grants have come up through the university through the outreach side of things, and also through there's a couple of funds that do funding of innovative education projects, which is what this has basically formed into. So a lot of the projects getting students involved cross-faculty tend to require extra cost overheads, and there are funds available for that, which I believe we've also tapped into as well. And I think we've had a couple of charitable donations that have helped along the way as well. Yes?
And ESA provides a free launch, I guess?
Yes, they do, assuming we... so we've done the selection process, and assuming we meet all their criteria and they're satisfied that the students have got what they need to out of it, then yes, they give us a free launch at the end of it, pending a free slot on their satellites, on their launches rather. So it's not a guarantee, that Q1, Q2 isn't a guaranteed date. It's next time they have free capacity, which they estimate will happen roughly then, might be longer. Yes?
It's really great to hear about the project. You know, I think congratulations getting kind of all of this done so far. It's come on a long way. Does it mean then that the mission itself will be under a UK flag, or will it fly under... how is your insurance liability going to operate? I apologise for that question.
Yeah, I have been asked that several times already this weekend. It will fly under a UK flag, and there are talks currently going on with the UK Space Agency to sort that out, and apparently it's looking positive. I don't know the specifics. I have tried to find out the specifics, and I've been told because nothing's concrete, they can't tell me yet. But the plan is that it will fly under a UK flag and be owned by the university and basically the University UK Space Agency partnership. I think, unless I may have used the wrong word there.
Oh, it sounds a perfect word to me.
But I'm afraid I don't know the specifics in that detail. I honestly don't.
Thank you. Thank you.
Any further questions?
I was very interested to see you're using polar coding rather than LDPC on the downlink. Can you talk a bit about the advantages of polar coding and how confident you are about it?
There's another graduate of Southampton, Matthew Breasure, who's been working with me on the electronics and the communications, and his background is in error coding research, and this is what he's been working on, and he is the subject matter expert on that. As far as I am aware, certainly for large blocks, it provides a performance closer to the Shannon limit than LDPC, in return for a lot more decoding complexity. But because it makes the numbers slightly better, and we've got masses of processing power to play with on the decoder, on the downlink, we're going to give it a go. We will, of course, be testing it alongside the LDPC and make sure that it performs to how we think it will perform. But we hope it will give us a little extra edge on the communications.
Okay. Any other questions? Okay. Well, Phil, thank you very much indeed for that. It sounds a really good project. I wish you luck with the UK Space Agency, and I hope we get a straight answer out of them as soon as we can. Would I like you to show your appreciation, please? Thank you.